Okay, welcome everybody in this room as well as in front of your computer or TV screen. So today we are gathered for the thesis defense of Shaobo Han. So I'm going to present myself first. I'm Xavier Crispin and I'm the supervisor of Shaobo. And we have here Simone Fabiano, who is the co-supervisor of Shaobo. So I'm going first to present the actor of today. So I will be the chairman. Rachel Segalman is the opponent. She's a professor at the University of California in Santa Barbara. Thank you for coming for so long and for a so short time. Then we have the evaluation panel composed of Dr. Carlo Xavier from the Free University of Brussels in Belgium. We have Professor Kajsa Uvdal from the Linköping University, as well as docent Daniel Hailey from Linköping University too. And we have also the start of today, Shaobo Han. And so I'm going to tell you a little bit how we have this morning. So Rachel is going to present the scientific context in which the thesis of Shaobo has been performed. After, we'll have Shaobo presenting his result, basically. Then we have a short break, 5-10 minutes max. And then we'll have a scientific discussion, examination with Rachel and Shaobo. And then after, we'll have questions from the evaluation panel and the audience. Okay, so Rachel, please, it's my pleasure to welcome you.
Pleasure to be here.
Yes.
Is this on? Can you all hear me? Yeah, mostly? Okay. So it's my pleasure to be here. One of the things that's interesting when you talk about energy landscapes and renewable energies is that we spend a lot of our time talking particularly about wind and solar as renewable energies. This data is from 2016 because it's the most recent available. One of the things that's somewhat depressing, actually, is that when you look at world energy use, it's almost all still the more classical coal, natural gas, and oil. And the reason is it's relatively hard to change infrastructure, right? And so not that we shouldn't try, but it's very hard to do that. And what that's telling you is that if you really want to impact the world, the right thing to think about is how we use the majority of the energy. Small changes in efficiency in our current use can lead to massive changes in the environment and in impact. So if the global power capacity is about 13 terawatts, I'm going to round that to 10 because I'm an engineer. The way we use fossil fuel type energy is we run it through a turbine, right? And the second law of thermodynamics says that if I want to create on order 10 terawatts of power, that I have to burn about 25 terawatts of a fuel to make heat, okay? And then the second law of thermodynamics says that only about 40% of that can become power. The rest is thrown away as waste heat, right? And so on this side, we can talk a lot about power efficiency. Can I come up with better ways to do the things I need to do, like heating and cooling, to make this part more efficient? But the other part I can talk about is that what this really means is that the steam coming out of a turbine is still really hot. It's well above 100 degrees Celsius. And that's actually what we're throwing away as the excess energy. If you couldn't put in a very inefficient device, even at 3%, on that fictional large engine, the amount of power you could generate is on the order of half a terawatt. That is approximately half the US electrical capacity, right? And so there's some very, very big wins to be made by thinking about what we can do with low-grade extra heat, okay? And that's a power engine, but it's also an application you can think about in smaller scale. For example, the battery in your computer gets quite hot, right? That is another place where we throw away a lot of energy. Putting in a small scale device there can actually have significant gains in your battery life, right? So these are very different ways of thinking about things than, say, just designing a new battery. So I would claim that that's an opportunity for thermoelectrics, which are devices that turn heat directly into energy. They are historically very, very reliable and very reversible. And what that means is that there are no moving parts, so nothing breaks. And And you can use them to both generate power from a heat source and also to heat and cool, right? So there are many applications for this. The problems have been that historically the materials you used to make this were things like bismuth telluride. They were both very expensive in their own right and very hard to process. So while these devices have been around since the 1960s, the two biggest applications were deep space probes. You take an element that's radioactive that decays at very high temperature, use that as your heat source, the vacuum of space as your cold, generate a fair amount of power, enough to run the electrical system of your deep space probe. And it's an application where no one cares that it's expensive, right? The probe is so expensive it doesn't matter. The other is that I drive a Prius. My Prius has seats that heat because it's resistive heating. If I drove a Porsche, my seats would also cool, right? Maybe not so necessary in Sweden in the winter, but fairly nice in the summer, right? But you also have to have a much more expensive car for that to make sense because these devices are quite expensive. So one of the questions that Shaobo will talk about in his defense is, how do we think about these kinds of devices to be made out of cheaper materials, right? So it's worth it to talk a little bit about why has this been so hard? I'm sure you'll talk a little bit too, just as a brief introduction. What he's going to talk about, I'm sure, is that we want a very high figure of merit. We want something that generates a lot of voltage, conducts power so that we can get the power out, and has a very low thermal conductivity so we can maintain a temperature gradient. And the challenge has always been that these relationships are in opposition to each other, right? We all know that, I'm just going to rush through this because I don't want to steal his presentation, but we all know that the oven mitt I use to take something out of my hot oven is thermally insulating. It's also electrically insulating. Almost anything we can imagine that is electrically and thermally insulating, almost everything that is thermally insulating will also be electrically insulating. So trying to get those two pieces to go in opposition is quite hard. Thermal power turns out to be exactly the same. So this is what many of the students refer to as the Bermuda's Triangle of thermoelectrics. It's very hard to break these relationships. But if we can make lower cost, lightweight thermoelectrics, even at relatively low efficiency, there are many applications we could jump into. I've already told you that we can put power in and cool things or heat them. We can also put temperature gradients across and get power out. What Shaobo will talk a little bit about is that we can also use these as sensors, right? They're designed to be materials that get big voltage contrasts as a result of a temperature difference. We can also use things like pressure to change the structure of the material and get a sensing signal out. And in this arena, really what we're talking about is not just the electronic function of the device, but figuring out how to put it into a 3D architecture so that we can make something large area, and lightweight and cheap so that it could be wearable, right? And so there are all of these extra constraints that come in when you're talking about wanting to make this something that either you wear as a t-shirt or you wear as a sensor on your arm that are not at play when you're talking about a deep space probe, right? And so if this is going to be next to your skin, there are many issues, some of which Shaobo will talk about, including the idea that it needs to be lightweight and cheap, but also the fact that you've got salts, because you sweat, and those can end up infiltrating your device. You've got water that could hydrate the material, and you've got that skin interface. And so it's very much a fundamental redesign of the material. So Shaobo's thesis will contain a chapter on mechanical and water stability, a chapter on the design of these as a sensor instead of as an electrical generator or cooler, and a third chapter on understanding environmental effects. I'm sorry, this is cutting out on your screen. So what underlies this is, let's move away from the expensive materials like bismuth telluride, and let's move into materials like organic semiconductors, which are very structurally similar to organic dyes, which indicates they can be made fairly inexpensively. And indeed, BASF is already making these things at least the kilogram scale. Various companies, including Fuji, have figured out how to print them to make large areas. And this is an example from Park, figuring out how to print them within a device architecture. So you've got all of the pieces printed and supposedly wearable. I'm not showing this, but a number of academic groups have started to figure out how to do these on Band-Aid type substrates. So you can actually wear them as a very lightweight component on your skin. A lot of the material that a lot of those applications are looking to right now is a material called P.PSS, which will be the backbone of Shaobo's thesis. It is one of the few commercially accessible conductive polymers. He will tell you, I'm sure, a lot about it, but one of the important things about P.dot is that it's sold as an aqueous suspension, meaning it's in water. So it can be coated over large areas and is fairly conductive. I'm showing you a small thermoelectric that we use to power a light bulb, just to demonstrate that it can be used over the kinds of applications that we care about. It's currently used in other applications like anti-static coatings, injection layers, and light-emitting diodes, which are much thinner films. And so developing these for large area, thick applications like thermoelectrics is one of the main issues that Shaobo will address. One of the interesting things is that when you're using it over thin areas, it's still fairly expensive as far as polymers go. That's what the market is right now. So a liter container is on order $1,000 to use in the lab. A truckload of polystyrene is €1 or $2, right? And so figuring out how to get it to the point where we can use it is one of the challenges, as well as how to make it really lightweight and wearable. So a lot of Shaobo's thesis will focus on adapting P.PSS to be used as an aerogel. So aerogels are materials that are called aerogels because 99% or more of the volume is occupied by air. And because it's occupied by air, and the density approaches air, and it gets some really interesting properties, it's nearly invisible to both optical wavelengths of light, as well as X-rays and various other techniques. So one of my favorite applications of this is a picture of it, is because it's fantastic, is a deep space probe again. So one of the early aerogels was encapsulating the deep space probe, and then they launched it. When they launched it, they expanded it into space, and they extended it into the tail of an asteroid. And the tail of the asteroid has dust, which no one's ever studied. The aerogel has so many pores that it absorbed the space dust. Then they packaged it back up and launched it at the Earth. Because we know trajectories fairly well, they planned for it to land in the Arizona desert. I have a friend who was on that mission. It turns out that if you were on the mission, you were allowed to take your family to camp in the desert, and they knew where it was going to land and watch the capsule land, right? And then what they did is they took this aerogel and they cut it into little pieces. And everybody who'd submitted and won an opportunity on that mission got a little piece of aerogel to take back and study, right? And the fact that it was invisible was important because you could put it in an X-ray beam line and study the dust and not worry about the material, right? The pores are about 100 nanometers in diameter, so it could catch relatively small pieces of dust. It has the physical properties of air and a manufacturable solid. So for example, it's a really good thermal insulator for a couple of reasons I'm sure we'll ask Shaobo, including the fact that it has a whole lot of density made out of air. And so it's sold as an insulator, that is a blowtorch and crayons on top. It's actually sold in very large areas as home insulation now. Part of what Shaobo will talk about is turning these into new applications. That's just using the fact that it has pores. If we use a conductive polymer as the matrix, can we get conductive properties out of it? Okay. And if we can do that, that creates a whole world of applications we're just beginning to touch, including self-powered sensors, wearable electronics. That's a very rigid one, but now we can start thinking about ones that look just like a bandage and are flexible and lightweight, and you could wear without feeling that you're wearing it. Same thing for various other kinds of medical monitors and other applications. Thank you very much.
Thank you, Roger, for the kind introduction. So now Shaobo is going to present his thesis. The title is Thermoelectric Polymer-Cellulose Composite Aerogels.
All right, good morning everyone and welcome to this seminar. My name is Shaobo Han And in the next 30 minutes, I'll be talking about what I have done during my PhD study. The title is Thermoelectric Polymer-Cellulose Composite Aerogels. The first part of this presentation will be motivations, then followed by the introduction of materials. Then in the result part, I'll be talking about two applications based on these materials. The first one is about a multi-parameter sensor, and the second application is about a solar steam generator. Let's start from motivations. So thermoelectric behaviors are direct conversion between thermal energy and electricity, and the applications of thermoelectric materials mainly include these three areas. So the first one is a thermoelectric cooler or heater, which transforms electricity to heat pump. The second one is a thermoelectric generator, which uses the temperature difference to generate electricity. And thermoelectric effect is also used in thermocouples as temperature sensors. So most of the studies on thermoelectric materials now are focused on inorganic materials because they normally have high thermoelectric performance. The organic materials also attached more and more attention during past years because of some unique features compared to inorganic materials, such as soft, which is very good for instance, making stretchable or wearable electronic devices. And most of the study on organic materials are about thin films because they are easily to be manufactured. However, also thin films also have usually have higher performance than thick films or bulk materials. However, in real applications, we normally need thick film or bulk materials. So in my PhD study, we focused on organic 3D materials called a thermoelectric aerogel. So basically, we use a thermoelectric polymer, this famous P.PSS, together with a 3D scaffold made by cellulose to make this elastic aerogel in two applications. So the first application is about sensors. And one example for using sensors is this electronic skin, which is an artificial surface which can detect, for instance, temperature, pressure, and so on. A typical electronic skin usually have these four parts. So firstly, you have sensors to record signals, and then you encode this signal and transform to a control system. But here we only focus on first part, sensors. So your previous studies on sensors usually have like different materials for sensing different parameters. For instance, here you have a pressure sensor, strain sensor, and temperature sensor for sensing these three parameters. So the strategy is like whatever signal you want to detect, you just add a new material to the device. It's okay if we're just interested to like couple of stimulus. However, in the future, especially with the development of Internet of Things, a huge amount of data need to be provided. Then the reading of sensors can be very complex. So there is a need for simplifying the manufacturing of sensors. So in this study, we investigated a possibility to use only one single material for sensing three parameters: the temperature, pressure, and humidity. I will be talking about it later. And the second application of the aerogel is about to produce more drinkable water in a cheap way, because we do need more clean and drinkable water. There are some data about the global water shortage in 2018. So over 800 million people lack access to clean water, and already more than 60% of humanity lives in area of water stress. And even worse, about 300,000 children under 5 die of illness directly linked to dirty water. So it will be good if we can help a little bit on such things for solving this problem. So now you might be curious that, okay, what kind of material can do such things? And what is the aerogel in the title, by the way? So let's talk about materials. So in short, the aerogels are made by polymers. There are plenty of polymers in our daily life, like plastics, rubbers, but they are mostly not conductive because there are almost no movable charge carriers, charges in them. However, the polymers can also be conductive. So the first conductive polymer was found in 1970s, which is this highly doped trans polyethylene. It has a so-called conjugated structure. In other words, it has alternating single double bonds on the polymer chain. Some of the electrons on such a polymer chain are delocalized, and by remove some of these electrons, so the movable charge carriers can be generated, so that the polymer becomes conductive. For instance, this highly doped trans polyethylene has the same conductivity with good metals. But it is unstable in air because it's very easy to be oxidized by, for instance, oxygen. But still, it was a great discovery. So after that, plenty of other conductive polymers have been found. One of them is this p-dot PSS, in which the p-dot acts as the electronic conductor, and the PSS here mainly act as a counter-ion for neutralize the doped p-dot. And the microstructure of the p-dot PSS is more or less like this. So PSS chains are very long with some short p-dot chain attached on them. And people like p-dot PSS because of many advantages. It has a high conductivity, it has good thermoelectric performance, and it's stable in air, and also it's water processable. That is because there are many sulfonic groups on the PSS chain, which are hydrophilic. The conductivity of p-dot PSS can be very different. The pristine p-dot PSS has about 33% of oxidation level, which is a typical semiconductor, and its conductivity is about 10 to minus 2 Siemens per centimeter. By dedope it, meaning that to give back the removed electrons, then we can have the neutral p-dot, which has much lower conductivity. We can also further increase the conductivity of p-dot PSS by a so-called secondary doping process. It is about to change the morphology of p-dot PSS, use some, for instance, high boiling point solvents, so that it can have higher charge carrier mobility. So that, for instance, this DMSO treated p-dot PSS can have conductivity about 1,000 Siemens per centimeter. So this is about p-dot PSS. Another important material in this work is cellulose, which is the main component of wood, and also it is the most abundant neutral polymer on Earth. So cellulose are extremely cheap and environmental friendly. And we can find cellulose fibers from, for instance, the wood cell walls, and a fiber is combined by some of the microfibrils, and each microfibril have some of the cellulose molecules. And these molecules are combined by some hydrogen bonds. So the mechanical property of cellulose is very good. So in this work, we use the cellulose is to provide a good mechanical property to the aerogel. Then what is the aerogel? So in short, if you can remove the liquid from a gel and without causing any shrinkage of the material, then you got an aerogel. So many substances can be used for making aerogels, and also the properties of aerogels can be very different, but commonly they all have low density and high surface area. Because of these features, the aerogels are mainly used in like these three areas. First one is a thermal insulator, and then a gas detector, and also the oil or dust absorbers. The aerogel in my PhD study, we call it thermoelectric aerogel because we have the thermoelectric polymer, PEDOPSS, which provide the conductivity and thermoelectricity to the aerogel. We also have the scaffold NFC, which is short for nanofibrillated cellulose, to bring the mechanical property to the aerogel. And importantly, we have a crosslinker called GOPS for the water stability and elasticity of the aerogel. I will be talking about it later. This is how we make the aerogels. We firstly put these three components together as a dispersion, and then do freeze drying, use liquid nitrogen. So at last, we got these sponge-like elastic aerogels, and the shapes and size can be controlled by using different modes, simply. So now I'll be talking about some results in the order of the papers attached on the thesis. In paper 1, we studied the effect of the cross-linker GOPS on properties of PEDOPSS. And paper 2 and 3 are about the first application of these aerogels, which is the multi-parameter sensors. And then the paper 4 is about another application, a solar steam generator. Let's start from paper 1. So as I mentioned above, the PEDOPSS is water possible because of the presence of sulfonic groups on PSS chain. It is an advantage of PEDOPSS, but sometimes we want our PEDOPSS product to be stable in water or in high humidity environment. So in that case, we need to improve the water stability of our products of PEDOPSS. One way to improve the water stability is to add some cross-linker, for instance, GOPS, to the PEDOPSS. These are two films of PEDOPSS, one without GOPS, one with only 0.1 volume percent of GOPS. If we put them in water, the no GOPS film will just disperse almost immediately, and the one with a little amount of GOPS can stay fine for a very long time. This is the chemical structure of GOPS. So on one side, there is an epoxide ring, which is reactive with nucleophilic groups, such as the sulfonic group of PSS. And on another side, there are three methoxysilane groups, which are reactive with another methoxysilane group from another GOPS in present water, so that the GOPS can be used as cross-linker. So in this work, we studied the mechanism of the cross-linking reaction and also the effect of GOPS on properties of PEDOPSS. Firstly, we studied the effects on the electrical conductivity of PEDOPSS, and the result clearly shows that more GOPS, lower conductivity. And conductivity depends on both charge carrier density and charge carrier mobility. So there are two possible reasons about the drop of conductivity. Either there is a lower charge carrier density, meaning that the doping level or oxidation level of PEDOT is reduced, so there are less charges. Or there is a reduced charge carrier mobility, meaning that maybe the number of charges are the same, but they are somehow less free to move. They are localized. What we wanted to study is which reason caused the decrease of conductivity, or maybe both of them work together, but we didn't know at that moment. So keep this in mind. We did some measurement and analysis. This is one of them is this absorbance spectroscopy. This black line is the signal from PEDOPSS film with all GOPS, and others are signals about increasing GOPS. So for PEDOPSS, if it's dedoped, meaning that if the oxidation level is decreased, we are supposed to see something like this. If it dedoped, for instance, by amine, we usually see a curve like this. So the peak at 850 nanometer should increase a little bit, and a new peak, a new obvious peak should appear at 600 nanometer. But it's not the case when we add gulps. So it looks like the oxidation level is constant. To confirm this, we also studied the chemical components of P-dot PSS films with different ratio of gulps with the XPS. This is the photoelectron spectra of sulfur 2p core levels. So it has two main contributions, one from P-dot, one from PSS. It shows that a signal from P-dot is not affected by adding gulps. And also, if the P-dot is dedoped, we should see a more symmetric doublet here. But it's not the case here. So it confirms that the oxidation level of P-dot was not affected. More information can be found from the PSS signals, and it also has two contributions, one from the sulfonic group interacting with the doped P-dot, and one from the sulfonic group interacting with some ions. And it clearly shows that what affected was the interaction between the sulfonic group with, for instance, the hydrogen ion. It is very likely due to the reaction between gulps and PSS. So based on this measurement and also some of other data, we summarize that the mechanism of reaction between gulps and the P-dot PSS is like this. So one side of gulps react with the sulfonic group on PSS, and another side react with another gulps. So eventually we got this cross-linked network, and the cross-linking doesn't change the oxidation level of P-dot. This is important. And what was changed is the morphology, so that it has lower charge carrier mobility. That's why the conductivity of P-dot PSS was decreased by adding gulps. So now we had a little idea about what's the relationship between gulps and P-dot PSS. And with it, we started the work in paper 2, which is about the temperature and pressure sensor of the aerogel. Then how we measure pressure and temperature use this material. So the material, the aerogel, is conductive. So by record the current with an changing applied voltage, we can get an RV curve like this originally, and the slope of the RV curve is the resistance. And because it's elastic, so when you press it, you change its resistance so that the slope of the RV curve can be changed a little bit. And also, because the P-dot PSS is a thermoelectric material, if we apply a temperature difference on two sides of it, then a thermal voltage can be generated so that the curve will shift to another position along the voltage axis. And this shift is the thermal voltage, which can be used to calculate the temperature difference. If we apply a temperature difference together with the pressure, what can happen is that the slope of the RV curve will be changed, and also the curve will shift to another position. So from the slope, we can calculate the pressure information, and from the position of RV curve, we can calculate the temperature information. That's how we measure temperature and pressure, use this aerogel. Based on that, we did this first measurement under different delta T. As we can see that under different delta T, the RV curves are located in different positions. That is what we want. But we also see a problem here, which is the slopes was also changed with the different delta T. So that the temperature affects the resistance of the material. That is kind of crosstalk, because in this case, if we got a change of resistance, it's difficult to know it's because of the change of temperature or because of change of pressure. is a crosstalk effect. This is because that the conductivity of pristine P.PSS is changing with temperature. Fortunately, the previous study already showed that it is possible to turn the P.PSS from a semi-conducting regime to a semi-metallic regime by the treatment of high boiling point solvents like DEG or DMSO, so that the conductivity of P.PSS can be independent with temperature, especially in room temperature range. What we did was to use the DMSO to treat the aerogel. We put the aerogel in a DMSO vapor environment for a while. So here shows some results. As we can see, after about 10 minutes DMSO treatment, the resistance of aerogel become independent with temperature in this temperature region. So then we used the DMSO treated aerogel. We measured some temperature difference again. And this time we don't see the obvious change on slopes. So that we removed the crosstalk effect by the DMSO treatment. So in summary for paper 2, the aerogel is able to measure temperature and pressure, and the temperature information can be calculated from the intercept of RV curves with the voltage axis, and the pressure information can be calculated from the slopes of RV curves. Importantly, the DMSO treatment removed the effect of temperature on resistance of aerogels, so it enabled the aerogel to measure these two parameters without crosstalk. In paper 3, the aerogel was designed as this branch-like structure because this time we want to measure one more parameter, which is humidity. And this structure alone is to have faster response to the humidity. We use the same strategy to measure pressure and temperature with the previous work. And this time, for measure humidity, we need a new electrical signal, which is the ionic thermal voltage. That is why we use P.PSS, because P.PSS is not only an electronic conductor, but also a good ionic conductor. For an electronic thermoelectric material, if we apply a temperature difference on it, we will see a voltage curve like this. And this open circuit voltage is the electronic thermal voltage, which is, however, if the conductor is also an ionic conductor, then once we apply a temperature difference, the thermal voltage will increase to a much higher position and then slowly come back to the same value of the electronic thermal voltage. The electronic thermal voltage equals to the electronic Seebeck coefficient times delta T. And the ionic thermal voltage equals to ionic Seebeck coefficient times delta T. What is the difference is that the electronic Seebeck coefficient is not changing with humidity, but the ionic one is changing with humidity. As we can see here, once if the humidity is below 50%, we don't see any ionic Seebeck coefficient. However, once the humidity increases to, for instance, 60%, then we see an obvious ionic effect. And this ionic Seebeck coefficient keep increasing with the humidity. And this feature allows us to also measure humidity with the aerogel. So how to measure it? In this measurement, we applied a same delta T at this moment, but in different humidity. If the humidity is low, then there's no ionic effect, thermal effect. So the voltage will increase to this level and just keep constant. And we can use this value to calculate the temperature difference. However, in high humidity environments, we see an ionic thermal voltage peak. If we got the temperature information from here, then this peak value is only depends on humidity. That's how we measure humidity. Then we also did some measurements under different temperature difference and different humidity. So once again, if we got one of these curves, from this area, we can calculate the temperature because here the value is only depends on the temperature. And once we got the temperature, then the peak value depends on the humidity. So we can go back to calculate the humidity. For measuring the 3 parameters, then we need a 3D paragraph. In the first state, there was no temperature difference, no pressure, so that we got these parallel IV curves. By the way, the axes are time, voltage, and current. So we also measure the IV curves. In the second state, at this moment, a temperature difference was applied so that the IV curves shifted to another position along the voltage axis. And in the third situation, an extra pressure was applied so that all the slopes of IV curves was increased. And in state 4, everything was measured in a high humidity environment so that the IV, once we apply a temperature difference, the IV curve will shift to a much higher position along the voltage axis and slowly come back. So from this, we can get the temperature information from this area. The humidity information can be got from this area, this value, and also the pressure, of course, we can get from the slope of the IV curves. So this is about the first application, the multi-parameter sensor. In paper 4, we studied a totally different application, which is a solar steam generator. This is a general solar steam generation system. So here is a warm house. The dirty water in it can be evaporated and condensed on the glass roof. And then the clean water can be used, for instance, to water plants, whatever. So in this process, the solar light is the only energy source, which is totally free. And also, all the particles and bacteria can be removed by the evaporation process. However, the water evaporation rate or the energy conversion efficiency is quite low if we just illuminate the sunlight into water directly, because water can absorb very limited energy from solar light. A promising way to increase the water evaporation rate is to add an absorber on top of the water, which can absorb much more energy. Of course, in this work, we use the aerogel as the absorber. And here shows some measured water evaporation rate in different situations. The unit is the kilogram per square meter. We measure it a long time. So in this, for pure water, the evaporation rate was about only 0.4. By adding the aerogel as the absorber, it was increased to about 1.2. However, it was not the highest value we got, because in this case, once the aerogel is heated up, the heat cannot be located just inside the aerogel. Instead, some of the heat will transfer to the bulk water and more or less be wasted. To solve this problem, we add an EPE foam as a thermal insulator in between of bulk water and the aerogel, so it can localize the heat just inside the absorber. By doing this, the water evaporation rate was increased to about 1.6. This is the absorbance of some of the materials. As we see, a film of PEDOT-PSS NFC component material cannot absorb all of the energy, but once the thickness is increased to 2 millimeter, then it can almost absorb 100% of the light. This is because the aerogel is kind of made by plenty of thin films of P.PSS. So if it's thick enough, then it absorbs all the light. And this is the mimic wormhouse for salty water destination. And the salty water was located in the middle chamber here and be evaporated through this aerogel. And because the salt cannot be evaporated after a while, actually this is after a very long time, it's become like this. Fortunately, the mechanical property of the aerogels are good enough for washing so that we can simply wash the aerogels and then reuse them. I measured some salinity of 3 source water and their purified water. The first source water is lab-made sodium chloride, which has a similar salinity with the average value of the global ocean. And the second one is a real seawater, which was collected from a bay of Sweden. And the third one is a tap water of Sweden, which is already drinkable. So we can see that the purified water, the salinity of purified water is independent with the source water, and they are all very low, and they are much lower than the good quality line of drinkable water. So we can say that the aerogel can be used as a solar steam generator for producing drinkable water. So in summary, in paper 1, we studied that the gulps act as a cross-linker which affects the morphology of P.PSS. However, the oxidation level of P.PSS was not affected. And in paper 2, we found that the DMSO treatment can remove the effect of temperature on resistance changing so that we can measure the temperature and pressure without crosstalk, use the aerogel. And in paper 3, we've studied the possibility for measuring 3 parameters, use the aerogel. And in paper 4, we found that the aerogel can be used as a good absorber of solar steam generator for produce drinkable water. And some outlooks. The mechanism of ionic thermoelectric effect is not very clear so far. So it's good to have more study on that. And also the reaction of gulps and cellulose, we didn't study that. And also you might already notice that the response time for humidity sensing is needed time. Like we have to calculate the temperature and then go back to calculate the humidity. And it takes about now like 15 minutes, which is quite long. I think it's good to reduce the response time. One promising way, I think, is to make smaller specimens because the aerogel that we use is like this size, it's very big. And it is possible, I think, to make smaller specimen by, for instance, a printing technique. And also, if we can print some smaller sensor matrix, then we can maybe use them to making some wearable electronic devices. And also, even the materials, like especially the cellulose, are very cheap. But we have to know that the freeze drying costs energy, which is kind of expensive. So if we can find a way to replace the freeze dry process, it will be great. At last, I thank my 2 supervisors, Xavier Crispin and Simone Fabiano. I also thank a lot of funding agencies, especially the China Scholarship Council. And I highly thank all the members of my lovely Academy family. Thank you for your attention.
We've made up our minds. We're going to do new. Do something else. Do more. Do the impossible. Do better. Do good. Do big. Do small. Do it wrong. Do it again. Do it ourselves. Do it together. Do what no one else has done. Do what will become big. Do the same. Do different. Do everything. Do something. Do new.